So if the pressure at the upper surface of the liquid is P naught, then at a depth h it is P naught plus rho g h. It varies from depth to depth. Now consider a cubical container open at the top. Okay, means the liquid is exposed to the atmosphere. Let's say the side of the container is A. Okay, now this is a side view. You can imagine a cube shaped container. In that liquid is filled. Assume liquid is completely filled up to the top. Right. Now you know how to calculate pressure in a liquid based on the depth. Fine. So if you consider this point, and let's say the depth of this point from the free surface is y, then the pressure here will be P naught plus rho g y. Depends on the depth. Now as a result of pressure, what happens? The liquid molecules will be trying to escape from there. Okay, you know that if you make a hole in the wall somewhere here, the liquid will flow out of it. Right? Because the molecules inside are under pressure, higher pressure compared to outside. Outside also there is pressure, there is atmospheric pressure from outside, right? So air molecules will be striking that place. I mean, that opening that is there, air molecules will be exerting a force there. But inside the pressure is more than atmospheric pressure. And a liquid or a fluid, whether it's liquids or gases, they always flow from a region of high pressure to a region of low pressure. Automatically they will flow. Okay. Why will they automatically flow? Now you consider a cylindrical element of the liquid like this. Suppose the pressure on this side is P1, pressure on this side is P2, then the force from this side will be pressure into cross-sectional area. Okay. And the force from this side will be this pressure into cross-sectional area. Now, on whichever side the pressure is higher, suppose P1 is more than P2, from that side the force will be higher. So automatically it will go to the other side. So fluids naturally tend to flow from a region of high pressure to a region of low pressure. So whenever there is a pressure difference, they will flow. Okay. So same thing happens here also. You know that if a hole is made, the liquid is going to flow out. Suppose the hole is not made, the liquid will still be exerting a force on the walls of the container. Okay, everywhere, wherever it is in contact with the container, it will be exerting a force on it. And you can calculate that force also. By definition, pressure is perpendicular force per unit area. Okay, you can write it as dF by dA also. Small perpendicular force acting on a small area. Okay, so you can say that the force exerted perpendicularly will be pressure multiplied with area. Or if you write it this way, you can write the small perpendicular force acting on a small patch of area is pressure multiplied with that area. And you integrate that, you can find out the total force also. So if you know pressure and the area on which that pressure is exerted, you can tell the force exerted on that area. Okay, so we'll work on that a little bit first. Right. So this liquid is under pressure, definitely. And because it is under pressure, it will be exerting forces on the walls of the container and also on the base of the container. Right. So we are considering static fluid itself and assume this container is in equilibrium. So it's not accelerated. The liquid is also not accelerated. Fine. First, calculate the force exerted by the liquid on the base of the container. Do this, both of you. Try to make use of pressure. Okay. Force force exerted by a liquid, not just liquid, even if it's a gas, force exerted by a fluid perpendicular to a surface is the pressure multiplied with area. Okay, pressure of the fluid multiplied with the area on which the force is acting. Okay, so based on that or using that, you calculate the force. Do this quickly. I'll give you 1 minute. Okay, I didn't get any answers yet. Let's see. The side of the container is given A, and you are asked to find out what is the force exerted by the liquid on the base of the container. And I already told you the approach also. Force is pressure, force exerted by liquid on a surface is pressure multiplied with area. Okay, we are considering ideal fluids now. So it won't exert any force parallel to the base. It will only exert a force perpendicular to the base. So pressure into area. One of you tell me, how much is the pressure in this liquid at any point on the base?
P naught plus rho G A, sir.
P naught plus rho Ga, correct. Because all the points are at the same depth A from the free surface. Okay, the side of the container is given A. That means the depth to the base is A. So all the liquid that is in contact with the base will be at a pressure of P naught plus rho Ga. Okay, you can name these points as A, B, C, and D. All of them will be under same pressure because they are all at the same depth. Now you may ask, does pressure not vary horizontally? In this case, it does not vary. Okay, the liquid is in equilibrium, right? You consider a cylindrical element like this. Suppose you want to know whether pressure at A is same as pressure at B or not. Consider a horizontal cylindrical element. Now, due to pressure at A, it will be experiencing some force. Due to pressure at B, it will be experiencing some force. But you know that part of the liquid should be in equilibrium, means these forces should balance, means the pressures must be equal at A and B. Okay. So that is the justification we can give to the fact that horizontally there will be no pressure variation in a non-accelerated container. Okay. Pressure at this point will be same as pressure at this point, because had the pressures not been same at the same horizontal level, that part of the liquid must have accelerated. It does not. Okay. Anyway, so the entire base is at a pressure of P naught plus rho Ga. Okay, then Vanilla, why could you not answer? It's easy only. No? Multiply that pressure with area of the base, you will get the force. That's all. So as a result of this pressure, the liquid will be exerting force on the base of the container this way. Okay. Due to pressure, force acts perpendicularly. So that force that is exerted on the base becomes pressure multiplied with area. Pressure is same over that entire region. It's a cube, so the base will be in the shape of a square. What is the area of that square? A square. That's all. That's the force acting on the base of the container. Is this clear to all of you? Any doubts in this? Pawan, did you understand? Okay, use of you joined in between. We were just solving a question based on pressure in a liquid at a certain depth. Okay, there is a cubical container in which a liquid is filled completely. The upper surface is open to atmosphere, and you were asked to find out what is the force acting on the base of the container. Okay, we are doing that through pressure multiplied with area. But see, all the liquid which is in contact with the base is at the same depth, it is at the same pressure. Fine. So the base basically is a surface which is under uniform pressure. If pressure is same everywhere, then pressure into area, pressure multiplied with area will give you the force. But the actual method, okay, to calculate force arising due to pressure is this. Okay. See, by definition, pressure is force perpendicular force per unit area. No. So you are supposed to write dF perpendicular. Force acting on a small element, small patch of area is the pressure on that patch multiplied with area of that patch. Okay. And then you will need to integrate all these to get the total force. And while integrating also, there is another catch. F is a force. While integrating forces, you need to make sure that all the forces are in the same direction. Okay. In this case, if you consider the base of a container like this cubical container, okay, I'll just give you an angular view. Suppose this is the base. Liquid molecules are in contact with it, right? Everywhere they are in contact with it. I'm just indicating a few of them. Wherever the liquid is in contact with it, it will exert a force. So all the small forces will be acting like this on the base. They are all in the same direction. Okay. Therefore, the total perpendicular force acting on the base can be taken as integral of df without bothering about the direction of the force vectors, because all the df vectors are in the same direction. Okay, which is integral pressure multiplied with small area. Pressure is same everywhere on the base, so you can put it outside the integral. P naught plus rho Ga multiplied with integral area of the base. Integral dA, which is a small patch of area on the base, becomes the total area of the base, a square. That is actually what we did. See, most books don't tell you this. They just say pressure into area, but actually this is the calculation. Okay, you have to consider force acting on every small element. Why is that important? In this question itself, see, we calculated force on the base of the container. That's fine. The base was under uniform pressure. That's okay. Now, see, you know that the liquid will be exerting force on the walls of the container as well. That is the next question now. You have to find out how much force acts on any one wall of the container. Okay. Just to help you understand better, let me draw one side wall. Okay. You can consider this as one wall of the container. Okay. It's completely filled with liquid. Right. So what happens on that right side wall is that wherever the liquid is in contact with it, it will be exerting a force perpendicular to the surface. But see, force exerted by a liquid is pressure multiplied with area. Now, on the base or for the base, the depth was same everywhere. But for the lateral wall, if you consider this yellow point, it is at one depth from the free surface. If you consider this blue point, it is at some other depth from the free surface. That means pressure will be varying from depth to depth on that lateral wall. And you know, as you go deeper, the pressure increases. So the force vectors, the df vectors that you show should be like this. Close to the upper surface, the forces will be weak. As you go deeper, the force becomes stronger. On the base, it will be the strongest. Like, close to the base. I should not say on the base. This is on the wall itself, but close to the base, the forces will be the strongest. Okay. So if you look at it from the side, if you see that wall of the container from the side, it looks like a straight line. And the force distribution will be like this. Higher up the surface, the forces will be weak. As you go down, the forces become stronger and stronger. Okay. But there is a slight advantage that you have here. On the entire wall, all the DFs that are there, small forces that are there, they may be varying in magnitude based on the depth, but they are all in the same direction. Okay, it's a flat surface, no? All the forces act in the same direction. So you can integrate DF directly without bothering about vector addition. But the challenge here is to first write an expression for DF. So based on the depth, at a certain depth, how much force does the wall experience? You have to write an expression for that and integrate it to get the total force acting on the wall. Okay, try this. I'll give you all 3 minutes. The question is to calculate force acting on any one wall of the cube or cubical container. Side is given A, density of the liquid is rho. Okay, try this, all of you. Okay, any answers, anyone? Right. See, the aim is to find out the or derive an expression for the force acting on the wall of the container. Why are we not able to directly do it? Because the pressure on the wall is not uniform. Okay, the wall is flat, but the pressure is not uniform, so we can't directly write pressure is force is pressure into area. Okay. Then what to do? First thing to do is to check how the pressure varies. Now this container is in equilibrium. So if the container is in equilibrium and fluid is static, the liquid is static, pressure varies with depth. But at a given depth, the pressure will be uniform. So what we have to do is identify small patches of area, elements of area on which the pressure is uniform. Now we know that pressure varies with depth. So if depth is same, means at a given depth, the pressure will be same everywhere. So what you have to do is consider an element. Consider a part of the surface which is at a fixed depth, somewhat like this. Okay. So I'm assuming the depth of this rectangular element. Okay, I can draw a proper rectangle itself. I'm assuming the depth of this rectangular element here that I'm shading is y from the free surface. And its height or its width, you can call it whatever you want. Let's call it dy. On that element, there will be forces acting like this due to pressure. Okay. These forces put together is what I will call as df, the force acting on a thin element. Why have I chosen an element like this? Because this element, I mean, all points of this element are at the same depth. Its width is negligible, no? Or its height is negligible, no? So not much pressure variation will be there over this element. So you can say this entire rectangle is under a single amount of pressure. How much is the pressure there? Because the depth is y, the pressure there will be P naught plus rho g y. That entire rectangular strip will be under the same pressure. Okay. Next thing we need is the area of that element. It's a rectangle. How do you write area of a rectangle? Length multiplied with height or length multiplied with width. Length here is the side of the cube itself, A, and the height is dy. So the area becomes A dy. Okay, so you need to get used to this, how to write expressions for, I mean, small elements, mass of small element, area of small element, volume of small element, length of small element, okay, such things. Okay, we know the pressure on the element, we know the area of the element. Multiplying them will give us the force acting on the element. Therefore, df becomes pressure there multiplied with area. Pressure there is P naught plus rho g y. Y is a variable. From element to element, y value keeps changing. Multiplied with area. Area is A dy. That's all. And we know that all the df vectors will be in the same direction because the surface is flat. On every element, the force will be acting in the same direction. Therefore, the net force on the wall is direct integral of df. You don't have to bother about the vector addition because all the vectors are in the same direction. So you need to integrate P naught plus rho gy multiplied with A dy. You can split this into two integrals. And what will be the limits for y? To cover the entire wall, y should be starting from 0 and the final value of y should be a itself. Okay, limits for y will be from 0 to a. That's all. Splitting this into two integrals, P naught is a constant atmospheric pressure. A is also a constant. First integral you'll be left with dy. P naught into a dy. P naught a are constants. Put them outside. Integral dy. Second part of the integral will be rho g a. These are constants. You'll be left with integral y dy. Okay. And limits from 0 to a, 0 to a. First part becomes P naught a square. Why? Because integral dy is y. And in that, if you substitute limits, it becomes a. So there's one a already. Integral gives you another a. A into a becomes a square. I have written it directly. I hope you can understand that. Second term, rho g a integral y dy is y square by 2. And then you substitute limit 0 to a. If you substitute upper limit, it becomes a square by 2. You substitute lower limit, it becomes 0. So effectively, it is a square by 2. So multiplying, it becomes rho g a cube divided by 2. That's all. That is the total force, expression for total force acting on the lateral wall of the container. Okay. So the challenge here was that the wall is not under uniform pressure. Pressure varies from point to point, then how to calculate the force. Okay, this is how you do it. Let's consider another situation. Consider a hollow sphere of radius r with pressure P inside it. Okay. So you can think of it as a round balloon. Okay. Or a bubble also you can consider. Right. So inside the balloon or the bubble, the pressure is P. Okay. As a result of that pressure, there will be forces acting on the walls of the balloon or the bubble. I want you to calculate or derive force due to pressure on one half of the sphere. Okay, just a moment. I'll help you all visualize this. So, see, obviously, it's not a liquid inside, it's a gas, air. Okay, and since a bubble is a small volume only, I'm not saying negligible volume, it's a small volume, not a great variation of height and all. You can assume the air inside it is at uniform pressure. Okay, so pressure everywhere inside the bubble is P. Okay. So don't consider pressure variation with depth from height to height. It's filled with a gas. The entire gas system will be under uniform pressure. Let the pressure be P. As a result of this pressure, what happens? See, it's gas inside. No, I told you yesterday that gas molecules will always be in random motion. Okay. At any temperature greater than 0 Kelvin, they'll be in random motion. So they'll be striking the walls of the container always. As a result, what happens? If you consider a small patch of area on the surface of this sphere, the gas molecules will be striking it from inside. As a result, it will experience a small force in this direction. Since the area we considered is small, the force acting on it also will be small. And not just that element, every element of the surface will be experiencing forces like that. And they will all be acting in a direction perpendicular to the patch of area that you consider. So there will be a dF acting here. There will be dF acting on this element. On every element, it will be acting. Why not? And so on. Okay. Now you can visualize the forces acting. Now, based on this visualization, you all tell me what is the net force due to pressure on the entire sphere? Anyone? Forces will be acting at every point of the surface. You visualize those forces and tell me how much you think will be the net force acting on the complete sphere.
Zero, sir.
Zero. Because there are forces, equal forces in all directions. No, their resultant will become zero. For every one force like this, there will be another force acting exactly opposite to it. Okay. On the diametrically opposite element, there will be a force dF acting like this, and they'll cancel. Okay. So all forces cancel. On the entire sphere, if you see, the net force is zero. But if you consider only one half of the sphere, okay, let me copy paste one half, just a moment. Okay, let us make use of these forces also. If you consider only one half of the bubble, okay, you can visualize a boundary here. It's a hollow sphere. So it's like a cup or a bowl kept sideways. There will be forces acting on every element here also, but the resultant of all these forces is not going to be zero. Definitely, it won't be zero because there are no forces to cancel on the other side, from the other side. Okay. So your aim now is to find out the total force acting on one half of the sphere. The radius is given capital R. Pressure inside is P. Everywhere the pressure is P itself. So if you consider the patch of area as dA, then you can write dF, force is equal to pressure multiplied with area. This is the expression for dF. Okay, and pressure is same everywhere. So I want the total force. So if I do it this way, it becomes integral P dA. P is same everywhere, so I can put it outside the integral and you will be left with integral dA. dA is a small patch of area on this hemisphere. Integrating all the small patches of area would become the total area of the hemisphere. Area of a sphere is 4 pi r square, hemisphere will be 2 pi r square. Then the total force acting on the hemisphere should be P into 2 pi r square. Do you all agree with this, or is there something wrong in this? Think about it, I'll give you a minute. Is this the total force acting on the hemisphere due to pressure inside it? Okay. Vanilla, why do you think this is wrong, or there is something wrong in this?
So the forces are in different directions, so we
Correct.
cannot
Correct. Correct.
integrate it.
Correct. See, force is a vector quantity. If you want to find out the integral of forces, okay. Now dF here is just the magnitude of the force. If you want to integrate forces, you need to, integration is nothing but summation. You need to add them by considering the fact that they are vectors. If vectors are in different directions, you can't simply add their magnitudes and tell that is the resultant's magnitude. Okay, that is the mistake in this procedure. dF PdA is correct only, but total force is integral PdA is wrong. Okay, you can't simply add the magnitudes of vectors which are in different directions and say that is the magnitude of resultant. Okay, only when vectors are in the same direction that works, which is what we did in the last problem to both parts of the last problem. Okay, so the issue here is that the forces df's are not in the same direction. Okay, then what to do? See, we had come across situations like this before also. I'll remind you one of them. Gravitation you take. We talked about gravitational field, right? We derived the gravitational field produced by a ring on its axis. What did we do there? We visualize the field produced by one of the elements. Okay, like this element dm that you take, it produces a field in this direction. Another element dm here produces a field in this direction. So fields produced by different elements were in different directions, and our aim was to find out the net field. What did we do there? Can any of you recollect and tell me what are the steps to be taken? Okay, what we did there was, see, field is a vector quantity, gravitational field. And the DE fields, the small fields, were in different directions. That was the challenge there. We could not directly integrate them to get the resultant. So the only option we are left with is to split them into components. Take the x components of all the small vectors, add them up. You'll get the x component of the resultant. Take the y components of all the vectors, add them up. You'll get the y component of the resultant. That is the way to integrate vectors which are in different directions. But we went a step ahead and we visualized the net field first. Because of, because the DE vectors were all making the same angle with the axis and they all had the same strength, we could determine that the net field is going to be to the left along the x-axis. So all we had to do there was integrate the x component of the field. The y components would get cancelled. We knew that. Only the x components will finally remain. So integrating x components was enough. So we derived the expression for x component of one dE vector and we integrated that. Okay. So remember this from now on. If you ever come across a situation where you have to integrate small vectors which are in different directions, integrate their x component separately, integrate y component separately. If required, integrate z component also separately. All their x components will be in one direction only, no? Okay, some may be positive, some may be negative, but they'll all be in the x direction. You can integrate directly. That's that. That is how you are supposed to proceed. Okay, you will have to do the same thing here also. The problem is that these forces dfs are in different directions. So you'll have to take x components and integrate them separately, y components integrate them separately. But let's see if we have any advantage here. Now you all visualize these df vectors acting on every element of the hemisphere. Okay. There'll be vectors acting everywhere on the surface. Can any of you tell me the direction of their resultant, if you can? If it's possible to predict the direction of the resultant, one of you tell me. Which way will it be?
Ashokit?
Can you repeat? Your voice was not clear. Just by looking at it, you can tell that the resultant of all these vectors is going to be to the right. This is the direction of net force acting on the hemisphere. Okay. Their upward components will be cancelled by their downward components. The components into the screen will be cancelled by components out of the screen. You have to visualize this in 3D. It's not a semicircle. It's not, yeah, it's not a semicircle. It's a hemisphere. Okay. So you have to imagine vectors in 3 dimensions. The resultant is going to be to the right. Okay. So for every vector here, all you need to do is the x integrate. All you need to do is integrate the x component. Okay. So basically, df was p multiplied with dA. You need df's x component. If you need the force as x component, okay, x component is to the right now. You will need area component in the yz plane. Okay, let us spend some time on this. It's quite easy to understand. Pressure is force perpendicular to the area divided by area. Okay, by definition, pressure is perpendicular force per unit area. Perpendicular to what? To the area itself. Okay, so if you want the force, you will have to write pressure multiplied with area. Which area? Area perpendicular to the force. Okay, force perpendicular to area perpendicular to force. Now, we have determined that the resultant of all these forces is going to be in the x direction. So we need to integrate the x components of these forces. X component of force will depend on area in the yz plane. Okay, like if you want force in this direction, it will depend on area this way. If this is the x direction, this is the yz plane. It depends on this area. Okay, so I'll just write it as yz. Pressure is same everywhere. So if you want total force in the x direction, you'll need to integrate small forces along the x direction, which is pressure multiplied with integral of area components in the yz plane. Okay. Now, I hope you can visualize how this sphere is arranged. The sphere is arranged, the hemisphere is arranged such that this is the x-axis and the circular base that it has is the yz plane. Okay. This is the y-axis and perpendicular to your screen will be the z-axis. So the circle, the base of the hemisphere lies in the yz plane. Okay. Now the actual area is a bulged area. It's 3 dimensional. It's not restricted to one plane. But the net force is in the x direction, right? So what we have to do is integrate the components of these area in the yz plane. So imagine projecting these areas onto the yz plane. Okay, that patch's projection will be here. Similarly, another patch, if you project it onto the yz plane, its projection will be here, and so on. So basically, if you project this entire hemisphere onto the YZ plane, can any of you tell me what will be the shape of the projection on the YZ plane? Like what I'm effectively saying is, imagine, imagine shining light from the right side. and there is a wall. The YZ plane is the wall. What is the shape of the shadow is what I'm asking.
Where, sir?
How will it be a square? Why will the border look like a square? I'm not asking one small patch of area. I'm asking complete hemisphere's projection.
A circle, sir.
It will be a circle, correct? The base of the hemisphere. Just a moment, I'll try to find a better diagram. Okay. So if you project the curved surface of a hemisphere onto its base, obviously it will become this circle. Okay. The radius was given as r. So this circle's radius will be r. Then the area of this circle, it will be pi r square. So if you integrate the component of area or the projection of area in the YZ plane, it becomes pi r square. Therefore, the total force acting on the hemisphere due to the pressure inside it becomes P into pi r square. It's not P into complete area 2 pi r square. Okay. So let me explain once again what we did here. You knew the pressure acting on a surface and you are asked to find out the force acting on it. Okay. From pressure, how to find out force? Force acting perpendicular to the surface is pressure into area. But the problem here is that the surface you were given is not a flat surface. So on different elements of the surface, on different parts of the surface, force acted in different directions. So to find out the total force, you can't simply multiply pressure with the complete area at once. Had it been a flat surface, you could have done that. Okay. So what to do here? First, write the expression for force acting on each element of the surface. Okay. Next thing we did was visualize the direction of net force. In this case, because there is a symmetry, it was easy to predict that the net force acts along the x-axis. Okay. Now, what is the cause of this force? Pressure. Force exerted by pressure acts perpendicular to a surface. Now, if force is on the along the x-axis, the surface that you need to consider is the YZ plane, is in the YZ plane. So to calculate that force along the x direction, you need to multiply pressure with area in the YZ plane. And imagine integrating all the patches of area in the YZ plane, you get the area of that circle, which is the base of the hemisphere basically. Okay. So actually forces are acting along different directions like this. But you know that the resultant of these forces will be in this direction. If you know that the resultant of the forces is in a particular direction, you need to take area perpendicular to that force. And the hemisphere projected perpendicular to that force becomes a circle. So that circle's area is what matters in the calculation of force. So if the pressure is P inside a bubble or a balloon, okay, which has a radius r, then on one hemisphere, the force acting will be P into pi r square. On the complete sphere, it is zero. That also we have visualized already. So is this clear to all of you? Are you understanding how to calculate force due to pressure? Any doubts in this? Okay. Right. So we did one problem where we calculated pressure on the wall of a base of a container, wall of a container, and then we took spherical container, uniform pressure everywhere. Right. Right. Now, yesterday we talked about how to calculate pressure with depth in case of a static fluid where the container was also in equilibrium. Let's consider a slightly different situation now. Now, if the container is in equilibrium, okay, the liquid will be Not liquid actually, the free surface of the liquid will be horizontal. It will settle like this. Okay. How did we derive pressure at a depth P is equal to P naught plus rho GH? We knew the pressure at the upper surface. Then we considered a point where we wanted the pressure. Between these 2 points means a point where we know the pressure and a point where we want to find out the pressure, we visualized an element of the liquid. Then we wrote forces acting on that element. Okay, vertical forces. Pressure here was P naught, so in this direction, P naught into area, that force will be acting. Pressure here is P, so in this direction, P into area, that force will be acting and its own weight will be acting. And you know that the element is in equilibrium. You wrote the equilibrium condition, means you balance the forces and you get this. Okay, that's fine. Now assume this container is accelerated. Okay, so that is the next part of this discussion. Variation of pressure in an accelerated fluid. Okay, or okay, let's not include gases, liquid itself. Now see, the liquid is static. What does static mean? With respect to container, it is not moving. Absolutely not moving. But the container itself could be moving. Okay, so first case, assume this container is accelerated upward with an acceleration a. If container acceleration is a, the liquid inside it also will be going with an acceleration a with respect to ground. With respect to container, it is at rest. But with respect to ground, both container and liquid will be going up with an acceleration a. In that case, I want you all to derive an expression for pressure at a depth y. Y or h, you can call it anything. Let's call it as y because usually we assign h to heights. So try this, all of you. I want you to find out the pressure at a depth y in case where the container is accelerated upward. You have to consider atmospheric pressure because the upper surface is open to atmosphere. So pressure here is P naught. You know the pressure at the upper surface at a depth y. Derive an expression for the pressure. Density of the liquid is rho. Do this, all of you. I'll give you all 2 minutes. Okay. Can any of you tell me an approach? What are you going to do? Or what are you trying to do?
Sir, first I draw the free body diagram and
You consider a cylindrical element,
yes, sir.
vertical element, or in any other orientation you took.
Vertical elements.
Okay. Let us do that. Consider a part of this liquid itself. We are not immersing any object into it. Whatever liquid is already there, we are just visualizing some part of it. Okay. You can take cuboid shape also, not an issue. It's not a rule that you should always take cylindrical. Fine. Let's say the cross-sectional area of this cylinder is A or dA. You can consider whatever you want. Here acceleration is small a. Don't confuse it with the side or anything. Okay. Yeah, Vanilla, go ahead. You drew the free body diagram. Tell me the forces acting on this.
So P naught into dA, this weight of the
Wait. P
cylinder
naught dA acts in which direction?
downward direction.
Okay. Due to atmospheric pressure, there will be force acting on the upper surface. So you consider it, yeah, you draw the free body diagram, consider it as a single point, that entire liquid. There will be a downward force of P naught multiplied with the area of cross section dA. Okay, good. Next.
And the weight of the cylinder
Weight of
downwards.
that part of the liquid will definitely be acting. How do you indicate weight? Or how do you express weight, not indicate?
So dm into g.
Okay, mass of the cylindrical element of liquid multiplied with G. Now, when it comes to liquids, we don't write mass directly. We use density and volume. Density is rho. Volume is area of cross section multiplied with the height. So that is mass multiplied with G. That becomes the weight. Correct. What other forces act on it?
The pressure into dA will act upon.
Okay. Due to pressure below, there will be force acting on the base of the cylinder, lower base of the cylinder, like this. That force acts in the upward direction. How much will that force be? See, the pressure on that base is P, area is dA, so P into dA will be acting upwards. Any other forces? Okay. After this, what will you write?
F net equal to M is
You want to write F net equal to MA and A is 0 or non-zero?
non-zero.
Okay. So basically, I mean, you have considered ground as the reference frame. You are observing that element with respect to ground. See, now, I mean, in this situation, there are two ways of writing equations. You can write equation means Newton's second law only. You can write Newton's second law for that cylinder with respect to container. You can also write it with respect to ground. But the equations will be slightly different. I mean, effectively, it will be the same, but the way you write the equation will be different because the container is now accelerated. So if you are writing Newton's second law on that cylindrical element with respect to container, you will have to include a pseudo force. If you are writing with respect to ground, no need to include the pseudo force. Okay. So with respect to ground, these will be the forces acting on that part of the liquid. So let me write that here. With respect to ground, you don't have to consider any pseudo force. So these will be the forces acting on it. And with respect to ground, along with the container, the liquid is also accelerated. So it has an acceleration A, it's not in equilibrium. So with respect to ground, if you write F net equal to ma, acceleration is in the upward direction. So you will consider upward force minus downward force. What are the downward forces acting on it? P naught dA is acting and its own weight is acting, rho g y dA. This is the net force, should be equated to mass into acceleration. Okay. Mass is rho y dA, density into volume, multiplied with acceleration A. Whatever is the acceleration of the container, with the same acceleration, the liquid also will be going up. Okay. Cancel dA throughout. And keep P on one side, send the remaining terms to the other side. You get P is equal to P naught plus rho y g plus A. Okay. And we are actually familiar with this. We know how to express apparent weight of an object which is placed in an elevator accelerating upward. Okay. If elevator is accelerating upward, effective gravity becomes g plus a. So wherever you have g, you write g plus a. If the elevator's acceleration is upward, same thing you do here. Had the container been in equilibrium, the pressure at a depth y would have been p naught plus rho g y. Okay, or rho y into g. Now because the container is accelerated upward, effectively the liquid feels heavier. Okay, so in place of g, you will have g plus a. That's all. So p is p naught plus rho g plus a into y. This is effective gravity. That's all. Suppose you want to write the equation with respect to container. Now the container is an accelerated frame of reference. You need to apply pseudo force. Can one of you tell me the basic formula for pseudo force? Basic formula for pseudo force.
So mass into acceleration of non-inertial field.
Yeah, mass of the object on which you are trying to on which you want to apply the pseudo force multiplied with acceleration of the non-inertial frame from which you are observing it. And direction of pseudo force. Pawan, can you answer? In which direction should we apply pseudo force? Pawan or Yusuf? Pseudo force should be applied in a direction opposite to the acceleration of the non-inertial frame. Here the container is the non-inertial frame, it is accelerated upward. So pseudo force should be applied in the downward direction. So weight plus this force plus pseudo force will be there. And what is the expression for pseudo force? Mass of the object on which you are applying it. So rho y dA multiplied with acceleration of the non-inertial frame. And under the influence of all these forces, relative to container, the liquid is stationary. It's in equilibrium. It's a static liquid, no? Along with container, it is moving, but inside the container, it is not moving. Okay. So with respect to container, the acceleration will be zero. That means it's in equilibrium. Therefore, force acting upward should be equal to sum of all forces acting downward. P naught dA plus rho gy dA plus rho ay dA. Effectively, if you cancel ds, you'll get the same expression. Pressure is equal to P naught plus rho g plus a into y. Okay, so whether you derive it by taking uh, by taking ground as the reference frame or the container as the reference frame, pressure will be pressure. Okay, so if the container is accelerated upward, then the pressure at a depth y from the free surface will be P naught plus rho g plus a into y. Just remember that if the container is accelerated upward, effective gravity becomes g plus a. So wherever you see g, you replace with g plus a. That's all. Okay. Next, I want Pawan or Yusuf to answer. How much will be the pressure at a depth y if the container is accelerated downward instead of upward? Vanilla, you can also answer, but answer in chat. Okay. Second situation. If the container is accelerated downward with some acceleration a, how much will be the pressure at a depth y from the free surface? Okay. Pawan, that's fine. If you cannot unmute, it's okay. But can you just tell me the idea? Like in chat itself, you tell. Vanilla, your answer is correct only. Okay. See, if the container is accelerated downward, the liquid inside it also will be accelerated downward. I want to share one condition here. The container is not accelerated so much that the liquid flows out of it. See, that possibility is also there. If you pull the container down very fast, liquid will come out of the container. That case we are not considering. The liquid is still static. Okay. So, assuming the liquid goes down along with the container. Then, see, if container is going down with an acceleration A, liquid also will be going down with an acceleration A. Now you have to write F net equal to ma by writing net force in the downward direction. How much is the net force in the downward direction? Its weight and force due to atmospheric pressure are in the downward direction. I'm writing with respect to ground. So weight rho y into dA, that is volume, multiplied with g. This is its weight, plus force due to atmospheric pressure, P naught into dA. These are the downward forces minus the upward force, P into dA, should be equal to mass into acceleration, rho y dA multiplied with A. That's all. You readjust this equation, you get P is equal to P naught plus rho g minus A into Y. That's all. When container is accelerated upward, G plus A is the effective gravity. When it is accelerated downward, effective gravity is G minus A. Simple. But there are cases here. As long as A is less than G, this is fine. If A is equal to G, if downward acceleration is equal to acceleration due to gravity, means the container is in free fall. Okay. Then this becomes zero. Effective gravity becomes zero. Effective gravity zero means the liquid will feel weightless. If the liquid is weightless, then pressure won't vary from depth to depth. The equation also tells you the same thing. pressure becomes P naught plus 0. That is P naught itself. Means the pressure everywhere will be same. So in a container which is, or in a liquid which is under free fall, pressure will be same everywhere because the liquid feels weightless. Okay. What if the acceleration is greater than acceleration due to gravity? Then it's slightly tricky actually. We'll discuss this in the next class. Okay, we need an in-depth discussion for that. If acceleration is more than g, whose acceleration? Container acceleration is more than g. Now liquid goes down due to gravity only, no? Gravity is what makes anything fall down. There's one more thing also here. Gravity is trying to pull the liquid down. Atmospheric pressure is also pushing the liquid down. Okay. Now let me just remind you what we had discussed in laws of motion. When a block is placed on the floor of an elevator, okay, if the elevator goes down with an acceleration greater than g, the only thing which can pull the block down is gravity. It's not attached to the floor of the elevator, no. So somehow if the elevator goes down with an acceleration more than g due to some external agent, the block cannot catch up with it. So as a result, what will happen? If the elevator goes down with an acceleration more than g, the block can only go down with an acceleration equal to g because its weight is the only thing which can make it go down. Then relatively, this is what will happen. Relatively, the block will appear to rise up inside the elevator. Okay, because block can only go down with an acceleration g. Gravity is the only thing pulling it down. Elevator is going down with an acceleration greater than g. Then some separation will occur between them. Here, when it comes to a fluid, there is a problem. What is the problem? Fluid cannot simply rise up like this. If fluid in a container tends to rise up, just a moment, I'll take another image. If fluid in the container tries to rise up, okay, or tends to rise up, what you get here is a vacuum, okay. There is no air, there cannot be air present there. When a block rises, there will be air below it, there will be air above it, okay. So from above, there will be atmospheric pressure into area acting. From below also, there will be atmospheric pressure into area acting. That's why we never bothered about that force. Atmospheric pressure is not negligible. By any means, it is not negligible. This is a significant force. But it acts in both directions. That's why we never considered the effect of atmospheric pressure on solids. Okay, while writing Newton's second law and all. But when it comes to liquids, that problem will be there. Air cannot come here, right, into this space. Air cannot enter. So the pressure there cannot be atmospheric pressure. It has to be zero pressure, vacuum. There's no gas. There are no molecules hitting the surface. So pressure there tends to become zero. If the liquid somehow manages to rise up, the pressure there is zero. But there is pressure above. So there will be force due to atmospheric pressure from above, but there cannot be force due to atmospheric pressure from below. So that pressure into area from above will be there. Weight of the liquid also will be there. Under the influence of both these forces, the liquid can accelerate. Only under the influence of weight, the acceleration it can get is g. But due to this force, it can manage some extra acceleration as well in the downward direction. Okay. How much extra acceleration can it manage? Force divided by mass. Okay. So g plus extra force acting on the liquid downward is atmospheric pressure multiplied with the cross-sectional area of the container divided by total mass of liquid in the container. That you'll have to find out based on the dimensions and all. Okay. So liquid can go down with up to this much acceleration, not more than this. More than this is not possible. Then the liquid will start rising up. Okay. So this is the maximum acceleration, maximum downward acceleration the liquid can attain. If the container goes faster than this, if the container accelerates faster than this, then you will see that gap appearing, this one. Okay, so this is a slightly complicated case. We'll discuss this in detail in the next class. But understand that It is possible for a liquid to go down with an acceleration more than g also, because atmospheric pressure will also be pushing it down. There is no atmospheric pressure from below, but from above it is there. Okay. We'll discuss in the next class. Next class will be on Thursday. Tomorrow, due to some reason, I will not be able to take a class. Thursday, you will have the next class. Okay. Same timings. Okay. Thank you also. What all did we discuss today? Let's quickly recollect. First thing we did was how to calculate force on a container based on pressure. Okay. These cases are important. If pressure is uniform and area is flat, it's very easy to calculate the force pressure into area. But if area is flat, but the pressure is non-uniform, you'll need to integrate. But integration is relatively easy because all the forces will be in the same direction. So no need to bother about components. Next case we took was pressure same everywhere, but the area is not flat. Okay. Then in that case, you'll have to visualize net force, take the component of area perpendicular to net force or projection of area perpendicular to net force. Then you will get the total force acting on the surface. We didn't take the case where pressure is variable and area is also not flat. That becomes too complicated. Let's not get into that. Not necessary also. Okay. After that, we started discussing variation of pressure in an accelerated liquid. We considered upward acceleration and downward acceleration. Downward acceleration, there is a little more left to be discussed. What if acceleration is more than g? And what if acceleration is more than this? This is the maximum acceleration the liquid can manage. But what if the acceleration of container is more than these cases? We'll need to work on a little bit more. We'll do that in the next class. And we will also discuss how to calculate pressure if the container is accelerated horizontally. Vertical acceleration we have discussed in this class. Next class we'll discuss horizontal acceleration. There can be a combination of both also. Okay. You need to know all this to understand buoyant force and solve problems based on fluids. Okay. Fine. Thank you all. We'll continue on Thursday.